Hello everyone, it's my pleasure to present our work Bench Reinforcement Learning through Continuation method. Bench Reinforcement Learning requires the agent to learn a policy pi to maximize expected return from a fixed set of trajectories collected by the behavior policy beta. Many real-world applications, such as recommender system or autonomous driving, fall under this setup. The policy optimization in bench reinforcement learning is challenging. Even with exact gradients, the objective function of expected return is hard to optimize because it may have many local optima. Furthermore, the gradient estimates of the expected return suffer from large variance when the learned policy pi deviates from the behavior policy beta. Therefore, we consider to restrict pi to stay close to beta with KL regularization. The new objective function is KL regularized expected return, where tau is the temperature, the weight of the KL regularization. We proved that in the tabular setting, with exact policy gradients, the convergence rate of optimizing KL regularized expected return is significantly faster than optimizing the objective function of expected return. Then we introduce the idea of continuation method. We can optimize a sequence of KL regularized expected return with decaying weight of KL regularization, and then trace back to the solution of the original objective function. In the simple grid world with sparse rewards, we assume there is exact gradients and the policy pi has bad initialization, moving away from the best reward. If we optimize expected return, the learned policy pi just gets stuck as a suboptimal solution for a long time. However, with the continuation method, we optimize the KL regularized expected return with decaying value of tau, and the learned policy quickly converges to the optimal policy. In bench reinforcement learning, we have no access to exact gradients, as it's hard to estimate the gradients. So we optimize KL regularized expected return with soft policy iteration. The algorithm alternates between soft policy evaluation and soft policy improvement and will converge to the optimal policy pi star tau to maximize KL regularized expected return with a temperature tau. We also prove that when tau goes to 0, the solution pi star tau converges to the solution pi star, which optimizes the original objective function. However, in practice, with a limited number of samples, the policy evaluation step in the soft policy iteration can be problematic. In this grid world example, we assume the behavior policy tends to move left and down. With a small value of tau, the learned policy pi deviates from the behavior policy beta, so it may visit the state action pairs rarely visited by beta, and the error in Q value estimation will propagate to the state action pairs frequently visited by beta. Then this error misleads the agent. The learned policy just gets stuck at a state with 0 reward. On the other hand, if we have a strong KL regularization, the learned policy pi stays close to beta and the error in Q estimation remains small. But the learned policy cannot be much better than the behavior policy because of the conservative updates. Our continuation method moves gradually between these two spectra. The value estimation benefits from the gradually relaxed KL regularization, and the error in Q estimation is small. When tau becomes close to 0, the learned policy pi aggressively improves over the beta, and so it always moves left to achieve the highest reward. The continuation method alleviates the problem in Q value estimation in the toy example, but in more complicated domains, the value evaluation is still problematic when tau becomes quite small in some cases. So we propose to use an ensemble of Q networks and monitor the variance of Q estimation in different Q networks. As we decrease the value of tau, if the variance becomes too high, we no longer trust the value estimation under the current tau and just take the policy checkpointed before we decrease to this tau as our solution. On the continuous control task, our method outperforms the baselines. On Atari games, also, the continuation method performs better in comparison to the baselines. To learn a softmax recommender on movie on the datasets with different quality and different sample sets, our continuation method performs consistently well. In conclusion, in this work, we propose a softboxing iteration through continuation method to alleviate the challenges in bench reinforcement learning. We provide theoretical ground and visualization to understand this technique, and we also empirically verify our method. Thanks for your attention and listening.